presentations here today. And then the first one is titled Towards Society 5.0, Cross-Industry Open Service Platform and Invitation to Innovation Bridge at Tokyo. And our speaker today would be Aika Yamashita. Thank you.
Good afternoon. This is Yamashita Aika from NICT. The presentation is Towards Society 5.0, Cross-Industry Open Service Platform and Invitation to Innovation Bridge at Tokyo. Beyond 5G is the next generation mobile communication system expected around 2030, and the future is the creation of new value through cross-industry services. However, architecture focused on this feature has not been successfully investigated. So to realize cross-industry services, it is necessary not only to advance elementary technologies, but to create a mechanism to connect them. NICT published the Beyond 5G 6C white paper. It shows the concept of cross-industry orchestration. In the bottom of this figure, there is a lot of system providers. To answer the request of service operators and users, we should pick up and combine different industries. This is the role of orchestrator. To understand the cross-industry orchestration, we also make three of orchestration stories: productive agriculture, reduction of CO2 emission, and the reduction of disaster risks. This is a part of productive agriculture. For example, one town overproduced onions while another faced a shortage of onions for school lunches. So orchestrator is checking traffic digital scene, and it found several drones are ready for immediate deployment. As a result, unused drones are deployed to transport onions to the school lunch factory. Like this situation, industrial collaboration can make things more efficiently. NICT's white paper is based on Society 5.0, which is the Japanese government vision. In the NICT's white paper also shows the architecture to grow the society sustainable. This is the POC system. We not only showing the ideas and architectures, we also doing and working for POC systems. This POC NICT is working for this POC system with some companies and institutions and labs and so on. This leads some international conferences and exhibitions and international standardizations. As a place to make POC systems and visions come through, NICT will open Co-Creation Hub Innovation Bridge at Tokyo in March 2026 in Tokyo. Innovation Bridge at Tokyo aims at beyond 5G and 6G R&D innovations and design technology systems and ideas from various industry fields. Like this figure, technologies, systems, and ideas will matching, harmonization, and inspiration each other at Innovation Bridge at Tokyo, and it will lead new projects, POC and showcases, and social implementations. Our key strategies are agile prototyping and field demonstration, communication buildings, and technology integration. This is a floor map of Innovation Bridge at Tokyo. There are Lab Lounge and Collaboration Lab. Lab Lounge is a place where stakeholders from diverse backgrounds gather for open and free discussions and inspiring new ideas. Collaboration Lab is a hub where technologies, knowledge, and experiences combine to create new value. Collaboration Lab includes digital twin rooms, international collaboration rooms, regional collaboration room, and agriculture room. For example, in agriculture room, we will grow something using AI or digital twin. Actually, at Innovation Bridge at Tokyo, some activities has already started. Agri-chain event discussed to realize cross-industry collaboration inspired by agricultural field. Zero Gravity event builds a community around Innovation Bridge at Tokyo and creating opportunities for collaboration within and beyond NICT. In these events, not only engineers or researchers is joining, but some various people from various backgrounds is participating. NICT presents our activities at major international exhibitions and conferences like MWC or Expo 2025. We look forward to collaborating with you. Thank you.
All right, so any questions for the speaker from the audience? Yes.
Yeah, this is a very good lab that you have and co-creation space. And maybe you could tell us more what can we collaborate with you, and maybe you can also talk a bit about the zero gravity event, why it is called that way, why it called zero gravity. You know? We know that the gravity is not zero. Okay, thank you.
Thank you for your question. First, at the Innovation Beach at Tokyo, we, as I introduced, there are some rooms, for example, digital twin or the international collaboration room or agriculture room. For example, now we preparing some POCs and it is open. So a lot of people gather at here and try some systems and we can discuss freely and open at Lab Lounge. This is introduce of Innovation Beach at Tokyo. And about why we call it Zero Gravity event, this is, we want to talk flat with people who has various backgrounds. So we named this event before building community as a Zero Gravity event. Thank you.
Is this place free to use by all, or we have to pay?
Yes, it is open. It is free and open.
Okay, it's an amazing place. You know, you have a digital twin that would be for educational purposes and mainly the digital twin area. So those would be like a kind of a virtual world that the people can go there and see the thing, and then, you know, for example, you want to open up a few things, the replica of what is exact in the real world. Yeah? Yeah. Just a comment, you know, this is a very, very good. Yeah, thank you.
Thank you.
Maybe I just thank you for your presentation. As same as Dr. Chief, however, any condition to join the innovation bridge? Any condition for partner or individual duo? Is there any condition or requirement?
Sorry.
No.
I think the question is, are there any conditions or requirements to join this lab?
Yeah.
Or anybody can join?
Yes, thank you for your question. Everybody can join this at this innovation bridge at Tokyo.
Yeah. Thank you.
Thank you.
Hi, I'm Kento Rishis from NICT. Actually, I'm a colleague of the presenter, and actually this place is open, but we need some contract actually. So we are still discussing what is the scheme, but I think, for example, collaborative research agreement, for example, we need to fix the goal to use this one. So maybe sooner or later, we will provide the scheme how to use this one. But I would really appreciate if you assume this area and propose some project and do something in this space. It's very good because it's a very, very nice place in front of the Tokyo station. It's we invite a lot of people from outside of NICT, so we can showcase the project with you. So it is really appreciated to propose any project. Please try to access me or the presenter. We can discuss, and we're really looking forward to do jointly. Yeah, thank you.
Yeah, one more question there.
Thank you for your explanation, because I see very, very interesting with cross-industry orchestration, and in my for me it's very, very important to have many data for any system, and so that we have to develop or to have a way to how to collect the data from different systems in the industry. Many industry you noted here, yeah? You showed in this, not only in power system, traffic management, and so on and so forth. So we need a lot of sensor device, for example. That means we need data, and how we can develop the platform for data collection is my suggestion only, not the question. Thank you.
Thank you.
Any other questions from the audience? All right, then we'll thank Yamashita-san. Thank you.
Thank you so much.
Right, the second presentation is TN-NTN, Convergence for Ubiquitous Connectivity in Future Networks. And the speaker, I don't need to introduce, he has been doing the emceeing for all day, but just for the sake of it, the speaker is Ernest Kunariwan from A-Star, Singapore.
Yeah, thank you very much, Chairman, and thank you very much, everyone, for this opportunity to present our work and to share with you the results. So in these presentations, I'll be sharing the project that we did on TN-NTN convergence for ubiquitous connectivity in future networks. So this project is in collaborations with NICT, and it was supported by IMDA Future Communications Programs under International Research Collaborations. So the background is we know that providing ubiquitous connectivity to connect the unconnected is one of the overarching goals in IMT 2030 vision of 6G. We know that using terrestrial network alone, we cannot provide the global coverage because we still have coverage holes, and especially in the areas like open sea for cruise ships, as well as in areas like mountains or deserts, terrestrial network cannot reach those coverage areas. On top of that, in the scenarios whereby the disaster occurs, can be due to earthquake, natural disasters, or it could even due to war, when terrestrial network infrastructures could be destroyed. In such scenarios, in order to bring back the communications infrastructures, non-terrestrial network is a key technologies. However, integrating non-terrestrial network and terrestrial network introduces its own set of challenges. So one of the most obvious challenges would be the heterogeneity of the quality of the links. Because NTN, you can achieve NTN using either aerial base stations or you can use satellites. So although aerial base stations can give you the flexibility of deploying new base stations at a very quick manner, due to the movements as well as the propeller, if it's based on the propeller, there's going to be a very high varying channel quality. And then if you talk about the geostationary satellites, although in terms of coverage, it can cover a very huge area, due to the distance from the ground, it's usually introduced a very significant transmission latency. Whereas if you talk about LEO, the distance is not as significant as GEO, but because of the high speed in orbiting the Earth, there's going to be a very significant Doppler spread introduced. So this heterogeneity of the links, coupled with the variations or different requirements for different UEs in terms of the QoS level that they need, bring about the challenge of deciding how are we supposed to allocate the users to which access platforms. And once we decide that associations, we also need to solve the problem of how we should allocate the different resources to all these different users. So this project is trying to address this very particular challenge, and we would like to propose effective methods to tackle the problem of user associations, resource allocations, as well as how best to place the aerial access point in integrated TN and NTN systems. So this diagram shows the illustrations of the systems that we considered in this study. So we have, on the ground, we have a few base stations installed, and also there's a number of UE that has to be served, and each of these UE has a different requirements in terms of QoS. So for simplicity, we consider two different groups of users. One group of users is EMBP users, means they require very high transmission throughput, but not so much on a low latency. And another group of users for the URLLC users, which prioritize on having a low latency transmissions, but not as high traffic throughput requirements. On top of these ground base stations, we also have aerial base stations, as well as satellite base stations. In terms of the frequency reuse, there's going to be interference within the access platform, as well as across access platforms. So here, in these diagrams that I showed, different ground base stations will have a frequency reuse, so there's going to be some interference among them. And on top of that, the bandwidth that's being used by the satellite communications is also shared together with the bandwidth that is being used by the ground base stations as well as the aerial base stations. So again, there are going to be some interference, cross-platform interference over there. Then, as I mentioned, what we are interested in is given a set of users with the different requirements, how we should associate the users to the different platforms and how we should assign the different resource blocks to them. So in order to solve that resource allocations problems, we formulate into these optimization problems. Of course, I'm not going to go through details into how this expressions is being formulated, but what I want to point out is that we introduce a few decision variables. So decision variables A is user association variables, means it's equal to 1 if the UE is assigned to a particular base stations. And we also introduce decision variables B, which is the resource block allocation banner variables. Another decision variables is the Q. So Q defines the locations of the UAV. And lastly, the coverage binary variable C would be to determine whether a certain user is within the coverage area of a certain base stations. And along with these maximizations formulations, we have a few constraints that we have to satisfy. The first constraint is to make sure that the UE can only be assigned to a certain G node B when it is within the coverage area, which is the basic requirements. So the second constraint is that the one users can only associate with one access platforms. So this is again for simplicity. We do not allow coordinated multi-point transmissions in this case. And the third constraint is to say that each resource block can only be assigned to one user. And here we do not allow advanced techniques like non-orthogonal multiple access. For the fourth constraint is the minimum data rate, so that the UE, when it's served, it can satisfy the QoS requirement. Constraint 5 and 6 is pertaining to the UAV to make sure that it's safe operation, so it doesn't exceed the maximum speed and it's not being too close to one another. Whereas constraint 7 and constraint 8 is related to the resource blocks that's being assigned. So in these projects, we propose two methods to solve that optimization problem. So the first one is to use multi-objective evolutionary algorithms based on diverse adaptive decompositions, or we call it MOEA DADE in short. This is an enhancement of the previous methods of MOEA-D. And for this enhancement, we are actually introducing three novel ideas. The first one is multi-strategy mutations, meaning throughout the evolutionary process of finding the best solutions, we allow the algorithms to change the mutation strategy. And this is based on the observations that depending on where you are at the solution space, a certain mutation strategy performs better than the others. For the second one is a distance-based external population maintenance, and this is to avoid being stuck at the local optimal that is not performing very good. And the third one is on sparsity-guided adaptive weight update, and this is to help with the convergence speed so that we can find the good solutions much faster. And in terms of decision variables, we use this factor X, which comprises of access association variables nu, resource block allocations omega, and UAV trajectory L. So this is the first method that we come up with. The second method that we come up with is to use a heterogeneous multi-agent deep reinforcement learning approach. So in this case, the illustration here shows that we simply assume that the each UAV and each UE is an independent agent that are performing on its own, and they're all interacting with the same wireless environment. They decided to take what's action next and observing the wireless environments to see what reward it's getting. So for the UAV, the state of the UAV is essentially the locations of the UAV as well as the aggregate throughput that the UAV achieved, considering all the UEs that's associated to it. And in terms of the actions that the UAV can take is the movement. So again, by right, UAV can move in any way they like, but in order to limit the dimension of the action space, we assume that the UAV can only take 4 different actions, so either move forward, backward, left, or right. And for the UE agent, in terms of the state of the UE, we define it as the experience data rate. And in terms of the actions of the UE is which G node B it should connect to, as well as how many resource block it should be assigned. In terms of the implementations, both the UAV agent and the UE agents is using the double dwelling DQ network, or D3QN in short. And the reason why we choose this D3QN is because first, it avoids instability issue that is faced in standard Q learning methods. Second is because it reduced the overestimations of the Q value by decoupling action selections from evaluations. And thirdly, it's also improved the value approximation stability by decomposing the Q functions into state and advantage functions. So these are the two proposed methods that we come up with in order to address the optimization problems that I showed in the previous slides. So the impact of this work, the benefit that we can get by using our proposed algorithms is that first, we can increase the number of users that can be served. So there are more users that can satisfy the required QoS. And second, we can optimize the utilization of the resource, both in terms of resource blocks as well as the utilizations of the aerial base stations. And thirdly, although we try to maximize as much as possible the overall throughput, we also take into consideration the fairness among the different users. So we don't want to maximize throughput while sacrificing some of the users. So in terms of output and outcome, this is the performance curve that we obtained from our first method with this multi-objective evolutionary algorithms. The leftmost graph is showing the Pareto trade-off. So in the x-axis, we have a normalized negative total throughput, so the smaller it is, the better. And on the y-axis, we have a variance of a normalized throughput. Again, the lower, the better. And we're comparing our proposed MOEAD-ADE with the original baseline algorithms of MOEAD. And just for completions, we also include the genetic algorithms, vanilla genetic algorithms in the evaluations comparisons. And as you can see, in terms of a Pareto front, the green line, which is our proposed method, is the one that's closest to the 0, 0, which shows that it's performing the best. The graph in the middle shows the average total data rate. So compared to the original MOEAD, we can achieve about 20% improvements in total data rates. And on the rightmost figures, which shows the normalized rate variance, which is essentially the fairness among the different users, we can achieve comparable fairness with the original MOEAD. Okay, so this one is the results that we obtained using our second method, which is based on heterogeneous multi-agent deep reinforcement learning approach. On the left-hand side, you can see the comparisons of the QoS success rate. And for comparisons, we use the vanilla deep Q learning network, as well as the greedy heuristics. And as you can see, the value of using the deep Q learning and the proposed heterogeneous multi-agent deep reinforcement learning is quite significant compared to the greedy heuristic algorithms. And then compared both the DQN as well as our proposed heterogeneous MADRL, for the low number of users, these two algorithms performs quite comparable. But as we increase the number of UEs to be beyond 50, we can see that our proposed algorithm starts performing better. And on the right-hand side there, it's just to show you that our proposed heterogeneous multi-agent deep reinforcement learning is able to converge within a reasonable time. So within 500 episodes, we can converge to the good solutions already. So in conclusions, within this work, we address the user association and resource allocation problems in integrated TN and TN systems. We propose two methods, one based on evolutionary algorithms and another based on a multi-agent deep reinforcement learning approach. And we show that the proposed method is able to achieve higher overall throughput, satisfying more users while maintaining the fairness among users. And in terms of future works, these are the things that currently we are trying to pursue, and we are also finding collaborations. So if any of you are interested in pursuing in any of these, feel free to talk to me. We can discuss further on how we can collaborate. So the first one is on integrated TN and TN-based resilient connectivity and sensing for smart maritime operations. So this is especially true in Singapore because Singapore is a global maritime hub. So we are planning to increase the capacity of our ports by almost like double by 2040. And we really need smart port operations with automations, and to enable that connectivity, ubiquitous connectivity is essential features to achieve that. Second one is intelligent network for universal integrated TN and TN. So this is looking at the trend right now because satellite communications that is operational right now are not based on 3GPP, and we know that 3GPP is coming. So in the future, we have kind of like expect that there's going to be a hybrid kind of connectivity whereby there will be modems that's able to connect to both non-3GPP and 3GPP satellite communication networks. And in there, how we can achieve a universal integrated TN and TN would be an interesting area to look into. So this includes like how we can incorporate AI for autonomous network operations, cross operators, roaming. All these factors will be dealt with within this work. And the third one is on 3GPP NTN terminal and MIMO in payload, incorporating multi-band, multi-beam ESA. So on top of the network side of innovations, we also need to innovate on the modem side. We want to have modems that's able to connect to multi-band with multi-beam, electronically steerable array. And finally, new architecture with cooperative swarm nanosatellite constellations is also one interesting area that we are considering. All right, so with that, I conclude my presentations, and thank you very much for your attention.
Thank you very much, Ernest. Questions from the floor?
Thank you very much for your presentation. In your work, you look at multi-agent scenario, right?
Yes.
For the second and the third layer, particularly the second layers, what's the constraint on the data rate or multi types of data? Because the drone now, they can transmit videos or some other data as well, right?
Yes. So within this study, we kind of like abstract that away. So the drones, we assume that it has a certain number of resource blocks. So resource block is a time and a frequency resources. In terms of constraint, what we wanted to ensure is the safe operations. So if you remember on the formulations of the optimization problems, I do put like the maximum velocity of the drones. So we make sure that it doesn't like travel beyond what it's capable of, and it's also the minimum distance. We have to ensure that two drones are not too closely to one another, otherwise it can be very dangerous, can collide, and the system might break down. But in terms of what each drone is capable of right now, because we don't do real like hardware simulations with the real base stations, so we just kind of like abstract them away. And in terms of how much throughput each drone can support, it's just based on the number of resource blocks that we allow each base station to assign to the different users.
So Ernest, you're talking about Dopplers and all those things in the beginning, right? So did you actually deploy any of these, or you're flying around drones, or this is just a mathematical exercise?
Yeah, so drones maybe not so bad. The Doppler is really a real problems when you talk about LEO. So LEO satellites, when they orbit the Earth, the speed is really, the Doppler is in terms of like hundreds of kilohertz, and that could make the communication link detrimental. But again, it's all theoretical. There's no like actual hardware simulations in this.
Okay, thanks. Anybody else would like to ask a question? If not, then thank you very much, Ernest.
Thank you very much.
And I guess that concludes the session. And Ernest, maybe you want to conclude the day.
Yeah, all right. Yeah, thank you very much, everyone, again, for attending these sessions. That will be the end for today. Yeah, thank you very much.